I know, I was very enthusiastically talking. Thank you. So hello, welcome to our webinar. We're excited that you all joined us. We have a poll question right up there. Did your library participate in the 2017 eclipse? We'll be talking and referring to the eclipse a good bit today because we are talking a lot about the sun. So as we're kind of letting people filter in, you can go ahead and participate in that poll. And also, you should see, let me get our arrow out here. Over here, there is a link bank. So we're going to be referring to a lot of links today. Different videos we're going to be showing you that you might want to have access to, different activities that we're going to be linking to, different NASA resources. So if you upload or download that link bank for Parker Solar Probe file, that will help you kind of find those links. We'll also have Greg in the chat box putting in links as we get going. So let me get that poll back up. Where did it go? All right, so we're going to launch another poll now. Actually, I have no idea where our first poll went, but this one is, will your library be participating in the 2024 eclipse? So I'm kind of anxious to see what the general reaction from the 2017 eclipse was. I know it's very far away. It's hard to even consider that, but yeah. I never want to hear the word eclipse again. We have one vote, yeah. We'll give you guys a few more seconds on that.
Your eclipse therapy programs.
Yeah. Jamie says we should do eclipse therapy programs for those of you that got called every day. All right. Well, we don't have a ton of time, so I'll go ahead and view, let's see, broadcast. View those votes. Okay, so most people say definitely. Some say I never want to hear the word eclipse again. Certainly understand. All right, so I'm going to go ahead and I'll do a just brief introduction. I'm joined here by Dr. Paul Dusenbery. Many of you may know him as our director here at the National Center for Interactive Learning at Space Science Institute. So if you've worked with us on a project before, StarNet, Phase 2, NASA at My Library, or even Project Build, you've probably met Paul. And many people don't know that he is quite a brilliant space physics mind. He's laughing right now that I said brilliant. So he's not just a wonderful boss and administrator. He's also a space physicist. So he's going to be presenting a good bit on the Parker Solar Probe and some of those Sun-Earth connections that we might not think about, and that actually would be kind of good content to talk about with kids and very accessible for kids. So we're going to start out like we normally do, with just a few little reminders and agenda for today. So yeah, again, resources, reminders, upcoming events. Paul is going to talk about the Parker Solar Probe. Then we're going to highlight an activity. It is called Solar Energy. I'm also going to feature a sample program that one of our NASA at My Library partners put on. I'm just going to kind of talk about what she did. She just sent me an email with, I put on this awesome Parker Solar Probe program. I want everybody to know about it. And so we're going to talk about that just a little bit. Next, Paul's going to talk about Sun-Earth connections. So how the sun and how the Earth interact and through solar winds. And I don't want to ruin anything. I'll let Paul get to that. And then we're going to move into a second activity. And we're going to talk a little bit about how you can repurpose some of those eclipse things that you did maybe this time last summer. And we'll, of course, end with a little Q&A. Oh, just to note, we are recording this webinar, as we always do, and we'll upload this to YouTube in about a day or two. So as always, most of you probably know about the Star Library Network, but for those of you that don't, the Star Library Network, otherwise referred to as StarNet, is our online community for librarians that are doing STEM. Would you say that? Is that a pretty succinct definition? Okay. So we have a lot of professional development resources, of course, our webinars. We send out a monthly newsletter chock full of great information. We have people participating in blogs, forums. It's where we link to our video resources as well. It's all free. So if you have not signed up, and we have it's about 9,000 folks have signed up or on our StarNet community of practice right now. So make sure to sign up for that. So these are our upcoming webinars. I know you guys are going to be so busy over the summer with summer reading. So we have these next 3 webinars, one each week for the next 3 weeks, or 4 weeks including this week. And then we'll, maybe take some of June and July off for you guys because I know you are going to be really busy and we'll be over at conferences. So next week on Wednesday, we're going to do Reaching New Audiences with Community Dialogues. Should be an S there. So Annie Holland will be joining me. Many of you know Annie Holland. And we'll also be joined by Zach Steer, one of our friends at the Boone Public Library in Erickson, Iowa. On Wednesday, May 30th, we're going to do Libraries Helping Girls Steam Ahead with NASA. So this is going to be put on, Andy and I will be up here doing our hosting duties. And then Emma Marcucci of the Space Telescope Science Institute will be joining us to talk about some of their resources and how you can get girls involved in STEM and STEAM. And lastly, on June 6th, a Universe of NASA Resources. We will be joined by a slew of folks from like JPL, NASA, Astronomical Society of the Pacific, I believe. That's right. Yeah. So we have a whole slew of folks, thank you, Ann, that will be joining us to talk about some of their resources, ways they're excited to get their free resources into libraries, and we're excited for you guys to be connected with them. So we're really excited about that one. Then, like I said, we may have some smaller webinars or project-specific webinars, but for summer, we know most of you guys are going to be really involved with summer reading. In the chat box, is anybody going to ALA this year, just next month?
To, what is it, Fat City? What's the name?
Is it the Jazz City?
Jazz City?
Yeah.
I don't know. And there's some name for
New Orleans.
New Orleans.
I'll be back.
Yeah, there you go.
Yeah. Not this time. So you will, let's see. If any of you are attending, please come see us. We'll be at the NASA booth, number 1839. If anybody was there last year, there was a ton of free giveaways, NASA stickers, NASA tote bags, NASA books. Yes, and we will have a button maker, so you can make a Space Cat button. Very excited about that. So we will be at that booth, pretty much the whole ALA session. But then we have 3 specific sessions that we will be leading. And you can see we have one back-to-back. We're still figuring out how we're going to get from each one. So STEM opportunities, resources, and partnerships with public libraries and after-school providers. Also on that Saturday, right after that, Tech Time Fun with Real-World Connections. And lastly, Annie's going to be doing lessons learned from the 2017 eclipse, what participation in charismatic events can do for your library. So this should be fun. If you've been to one of our conference sessions before, I like to think they're a lot of fun. We usually have some type of hands-on activity and food and a lot of laughs. So make sure to join us. And of course, the Clearinghouse. I mentioned this a lot, and you probably all know the Clearinghouse will be referencing activities. The Clearinghouse is where all of our STEM activities that we think are great for the library setting, where those live, per se. So this kind of just shows you the outline of it. But I want to highlight this new feature that we just integrated in the Clearinghouse, and it's called STEM Tools or Add a Tech Time Twist. So for a lot of activities that you can do out there, you can add maybe, if you have a $20 piece of equipment or a $40 piece of equipment, that can really enhance an activity. And we don't want to list that, an activity requires that per se. We don't want to, scare anybody off thinking this is a $50 activity. No way my library can do that. So this Tech Time button will kind of highlight whether you have to have a STEM tool that might be prohibitive for some libraries. So whether a STEM tool is required. And by STEM tools, we mean something like a microscope or an infrared thermometer, or maybe a tablet or magnetometer, or something like that. But for a lot of these activities, no, you don't need one. You can still do the activity without a STEM tool, but it is very helpful. So we've added this section down below under the Add a Tech Twist button. That's where we're going to talk a little bit about what that actually is. So the solar energy activity we'll be highlighting today, and we'll come back to this. But just to let you know that we are, spicing it up a little bit and making it a little bit more accessible for you guys. All right, so I went through that pretty quickly. Oh, I failed to mention we also have another brilliant space physics mind in the room today, Mr. Jamie Harold. I don't know if you can see his hand. Yeah. Unfortunately, today he's not going to be talking about space physics. He's pretty much relegated to being our cameraman and our safety czar. So just know that he's here, and he may be able to answer some of your questions too. So Dr. Paul Dusenbery, I won't give him too much of an introduction. Many of you may have known him if you've worked with him or if you've been on a project, like I said. But just wanted to highlight that he does have a pretty extensive background in physics. He is the founder of the Space Science Institute, where we all work, and he's the director of the National Center for Interactive Learning at the Space Science Institute. So NCIL is a division, if you will, of NCIL. Without further ado, I think Paul wants to talk a little bit about what makes the Parker Solar Probe so special and what makes, the sun so special. So I'll turn it over to you, Paul.
Thanks a lot, Brooks. Wow, that's a fun. Just remember that time I was back at the National Science Foundation for a couple years as being they call it a rotator, but I was in the magnetospheric physics program, and it just happened that NSF back in those days was just a few blocks from the White House. And it happened that also that the Education Human Resources Directorate, basically the education part of NSF, was just down our hallway. And because of that, for one thing led to another, and I happened to walk down there one day to talk about education things and how we can help maybe with exhibits and things like that in some of the museums around DC, and that's really where it all began for me in terms of moving away from scientific research on what's called plasma physics into education areas. So that was a very important moment in my life. Well, I think all of us would agree that looking up at the heavens, looking out at stars and maybe seeing some cool planets, and of course our very own moon in the night sky, we start thinking about where are we in this amazing space that we call home, in this universe that we call home. And one of the big important things in there, of course, is to understand our sun, which is a very close-in star. So let's, maybe the next slide, I wanted to just have a little fun here. So I will start this off, but I need everyone's help. So Brooks, why don't you let everyone know about the fact that moons, we have our own moon, but moons orbit planets, and there's many moons around planets like Jupiter and Saturn. Earth has just one, but how many, so what's the next thing? So if moons orbit planets, what do planets do? What do planets do? So planets do what? We're going to go down into that lower left panel in just a moment, but okay, so that's it. So let's go ahead, and you're all very, very sharp today, it seems like to me. So planets orbit stars, and our planet and the planets of the solar system all orbit a star we call the sun. Well, if planets orbit stars, what do stars do? Are they just left out there just hanging around, not doing anything? Well, they do something too. So what do you think stars do similar to planets? All right, wow, there's some interesting comments down there. Yeah, okay. I like that. Yeah, absolutely. Stars can twinkle mostly because of our atmosphere, I believe. I don't think they actually twinkle, but maybe a few do. Anyway, let's go ahead and go up there, Brooks. Stars orbit the centers of galaxies, and I don't know if you know this or not, but there's a massive black hole at the center of our galaxy. It's 10 million times the mass of our sun, so it's a monster black hole. So don't go there, please. But our sun is orbiting. This takes about 200 million years, I believe, for our sun to orbit around the galaxy. And then finally, what do galaxies do? So you can go ahead and do something in the chat, but really galaxies kind of orbit each other in these massive, huge, vast regions called clusters. And then there's 100 billion galaxies roughly in the universe. So there's a lot of galaxies there. Okay, let's go ahead and move on. Now, in the night sky, there are thousands of stars, and you can see those with binoculars, naked eye views, also telescopes. Go ahead. And what I want to have you think about, though, all these stars in the galaxy, there is one that's very, very special to us. It's about 276,000 times closer than any of the others. Maybe you can think about what that might be. All right, go ahead. All right, here we go. With the drum roll. There you go. It is our very own star, which is a very special thing. Anne's going to talk to you about charismatic events if you happen to be at ALA. But this star is sort of a charismatic object, I think. It's a very important object that we learn all about, not only how it behaves in our solar system, but also about other stars like it. So let's move on. Because it's so much closer than all the other stars, we can find out a lot about stars by studying the sun. Okay, so next is a little bit about where our sun is located. Luckily for us, we're not near that 10 million mass, super black hole in the center. Brooks, why don't you show us maybe with your pointer? We're out about 2/3. Go ahead and click on somewhere around there, I think. So that looks good. We're not really close to the center, which is very good. So go ahead and click a little bit. There's a few bits of text there that can remind everyone, and then there's one more, I believe. There we go. So sometimes if you ask children about how many stars are in our solar system, they might say that there's lots, because that's what they see when they look up at the night sky. They see all these points of light, and people tell them, hey, these are stars, and so we must have lots in our solar system. But they happen to be really, really, really far away. We only have one star in the solar system, and that happens to be our sun. And our solar system, and just like Brooks pointed out, is about 2/3 of the way out from the galaxy's center. Okay, the next slide is now about this Parker Solar Probe mission. So, and this could be one of these charismatic, events. Maybe the launch. I'll show you a really cool picture of the launch vehicle for this mission. But this is a very important mission. They call it extreme science or extreme exploration. Why? Because it's going really close to our star, which happens to be rather hot. And so they had to solve all these important engineering challenges to be able to get a spacecraft from Earth to the sun and to survive its journey and to survive its discovery phase. Okay, let's go ahead and look a little bit about, I call this some cool facts, but these are pretty hot facts actually. So it's going to go within about 4 million miles of the sun's surface. No other spacecraft has ever done that. They're going to be faced with lots of heat and radiation, particle radiation, solar radiation, light radiation. It's just going to be really amazing event, I think. The launch window is at the end of July and about the middle of August. I wish that we could say to everyone, hey, the mission's going to launch exactly at this time on this date, but that rarely happens. NASA always does launch windows, and sometimes, for whatever reasons, it could be malfunctions, or they want to change something on the spacecraft, they have to delay it.
Or poor weather.
Poor weather easily could be a way for them to say we're going to scrub the mission or the launch this date and then come back maybe in a couple days, kind of a thing.
So Paul, people might be looking at that and they think 4 million miles. It's not that close. But I read earlier the closest we've been to the sun is 28 million miles.
Yeah, I think that's right. We had a mission that went to Mercury, and that's about 35 million miles away, I think. That's the closest planet in the solar system. That was an amazing mission, but this is going to within 4 million miles of the surface, which is pretty amazing, when you think about it. And you might ask yourself, why is that December 24? Is that a typo? Well, there's lots of things happening in the year of 2024. I think we just mentioned that there's going to be an eclipse.
That caused the eclipse.
Oh, yeah, right. There's going to be I looked up on, I looked at some data, and the sun is going through its maximum activity stage at about that time as well. So the sun will be very active with all these big storms that are going to be launched from the surface and that sort of thing. And then, of course, the solar probe is going to arrive in its discovery orbit around the sun in late 2024. So mark that on your calendars. And you might look at this next one. I think this is pretty cool. 430,000 miles per hour. I hope none of you drive your cars that fast. If you do, make sure that you're buckled up. That is really fast. And it's something like 125 miles per second, which means that you could fly between Philadelphia and Washington, D.C. in 1 second, just for those who are on the East Coast who do that kind of thing.
So for all of you doing some quick math in your head, so we know, would anybody like to say in the chat box how far the Earth is from the sun, if you know that off the top of your head? How far is it from the Earth to the sun?
Cool. So
Annie, okay.
What did Anne?
Anne said 1
Oh,
astronomical
very
unit.
clever,
Yes.
Anne Holland.
Yes.
I don't know.
Well, it's about 93 million miles, right? And so I was doing the math and I was thinking, oh, 500,000 miles per hour, so it should get there in, I don't know, 180 hours, something along those lines. And Paul, you mentioned though that not to think about it as a straight path.
No, it's not as the crow flies, so to speak. These orbits, and this is true for most space missions, they have to go orbit and orbit and orbit around the sun, getting closer and closer in every time they do that. And they're using the planet Venus, which is about the same size as Earth and same mass as Earth, as a pretty good gravity assist object. And so they're using it's a slingshot effect as they go by, and they pick up a little bit of, or they slough off energy, and they get a little bit tighter and tighter and tighter. And that's why it takes so long for them to get into the orbit that they want. You would think that they could just do it in less than a year.
Yeah, right.
But that's not how it really works. They got to park themselves into this amazing orbit that they're going to be turning their instruments during that part of it. And I wanted to just mention that one of the neat things about this is a thermal engineering feat that they're able to create this 4.5-inch thick carbon composite shield to be able to protect the instruments as they do their instrumenting, so to speak. And so this is going to be, they've tested it, and the next slide actually shows a little bit of this shield, which I thought was kind of cool. And there are these engineers, these are all engineers probably, at Goddard Space Flight Center. They're lowering their shield into the test area. They're going to leave this chamber. It's a huge chamber. They're going to evacuate it, create a pretty good vacuum in there, and then they're going to run all sorts of tests on it. So they have studied and worked, engineers like to do this over and over again to make sure that everything works perfectly. So that's this heat shield that's really cool, and it's going to allow the spacecraft to get that close to the sun. So let's go ahead and go on to the next. Oh, this is one of my favorites. Doesn't that look magnificent? This is a Delta IV heavy launch vehicle that's going to be launched at Kennedy Space Center. As we mentioned, it's going to be launched hopefully at the end of July or beginning of August of this year. And if it's at night like this shot is, that's even cooler. There'll be a lot of people visiting the Cape, scientists, engineers, and VIP people, the press is all going to be there for this big launch. And we would love libraries to be excited about this too, and maybe stream some of the launching from your library. And while you're doing that, or as part of this, you could do a neat program with hands-on activities related to the mission theme, which is exploring our sun.
So, Paul, can I interrupt for a couple of things? Andy asked, do you think, is that composite shield, that 4.5-inch shield, is that going to protect the electronics from like flares and maybe some type of solar interference?
It's supposed to protect everything.
Okay.
Yeah, I mean, that's what's so amazing about it. And they bombarded this shield with high energy particles from different sources, and they put it under all sorts of thermal tests, and oh my gosh, they've shaken it and done vibration tests and things, and they think it's going to hold, but nobody has ever done this before. That's why NASA and other space agencies like the Europeans are really at the forefront here of going into what some people call extreme exploration. What do you think of that term, Brooks?
Sounds pretty extreme to me.
Pretty.
Yeah. And we had another question here from Jeanette, and I think I know the answer to this, but it's, can we create heat that high that is man-made? Jamie, I'm looking at you. I saw that you were typing. I'm going to say yes, I believe that we can.
Yeah, I mean, we can actually create temperatures high enough to generate fusion just like the sun does. We tend to put more energy into doing that than we get out from the fusion, which is why you don't have a fusion power plant yet. But we can totally do it.
Yeah, great. Yeah.
And my last little note is that when we were talking about the trajectory and the orbit of Parker Solar Probe, I found a good video this morning. Greg, if you can include it, it is in that link bank I have up there that you can download. Gosh, I forget the exact name of the video, but it starts with heliophysics, I believe, and it's a video showing the trajectory of the Parker Solar Probe and the Solar Orbiter, which will launch in 2020. And we don't want to talk about that too much because we want to have a webinar for that in 2020, I'm sure, too.
I'm sure.
Yeah.
Okay, good.
All right.
So I think we're going to show a video.
We
aren't
are, yeah.
Okay, so we'll see if this works. This is a fairly short video, and somebody mentioned that it may be hard for libraries to have a viewing event for the launch without a definite. I totally agree with you. That's something that we all have to kind of work on, but we'll have to see how it goes. But, the solar eclipse was really nice because it was a definite date, a definite time of the day.
Right.
Everyone can really, they could plan well in advance for that. These other kinds of NASA events like launches are challenging because of that launch window effect.
NASA really scheduled that one well, didn't they, Paul? The eclipse.
Yeah, right. NASA.
So we're going to show you a video. This is the trailer that NASA put out for the Parker Solar Probe. If you have maybe not a great internet connectivity, it might be hard for you to stream this through the Adobe Connect system. So Greg, if you could pull the video of this out of the link bank, and for those of you that have the link bank, it should be in here. It is the Parker Solar Probe trailer video. So I've let it buffered. It should show. If it stops or something, you can access it via YouTube. All right.
NASA's Parker Solar Probe mission is about to embark on a historic journey to our very own star, the Sun. Named for Dr. Eugene N. Parker, whose contributions have revolutionized our understanding of the Sun, Parker Solar Probe will usher in a new era of exploration. It's a mission of extremes. The spacecraft will plunge through the Sun's atmosphere, called the corona, and fly closer to the Sun's surface than any spacecraft in history. More than 7 times closer. The Sun's surface is hot, at temperatures exceeding 10,000 degrees Fahrenheit. But the real surprise is, its atmosphere is even hotter, 300 times hotter. Facing the corona's brutal heat and radiation conditions, Parker Solar Probe will finally provide answers to some of the most important questions about how our Sun works. As Parker Solar Probe speeds around the Sun making these measurements, it's moving at over 430,000 miles per hour. That's like traveling from New York to Tokyo in less than a minute. This mission is the culmination of 60 years' work by the best and brightest scientific and engineering minds. Today, our technology will let us achieve our dreams, to reveal the secrets of the corona and our Sun, and to one day help better protect technology from the threats of space weather. In 2018, we will launch Parker Solar Probe, humanity's first mission to touch the Sun.
All right. It's just inspirational music.
Whoa, that's pretty inspirational.
Goosebumps, Paul.
Yeah, I know. I love that music, and I think Jamie even liked the narrator on that.
I think he did.
Yeah.
Be a nice thing. All right.
Excellent.
So, Paul, you've introduced Parker Solar Probe, and it's undoubtedly you have a lot of knowledge on solar energy. I'm going to need you to kind of just erase all that knowledge in your head. You're going to be my my model patron for this activity.
Wonderful.
And so I showed you that solar energy activity earlier, and we're going to kind of just talk a little bit about it and talk about how you could integrate this into your programming. So the first thing you could bring up, and this whole concept is it's about the idea of albedo and the fact that darker materials absorb more heat and lighter materials reflect more heat. So I pulled a few images here, and I want you guys to let me know who looks more comfortable in this picture. Option A or option B? Which one of those people do you think looks more comfortable? Yeah, I'm going to say option B. I don't know. Option A, he might have some other stuff going on in his life.
What's going on?
I don't know.
What's going on with that guy?
Yeah. So that is a visual, you can show to your patrons, or I just pulled these images from Shutterstock. Or you could ask them, like, hey, friends, have you all ever been outside on a hot day and you're wearing a dark shirt and you just feel really, really hot? So make some connection like that with your patrons. Make them think about a time when they have been hot outside in a dark shirt. So I'm going to get real sciencey with you momentarily. When we get solar radiation, energy that comes from the sun, not all of that stays on Earth. So a lot of that hits the surface of the Earth and gets reflected right back. So I like this graphic. It shows that some of our solar energy coming on Earth, it gets reflected in our atmosphere. So it gets reflected off of those clouds. And then we see over here, it's getting reflected off of the snow-capped mountain or glacier or iceberg. And then over here, where we're in ocean water, that energy, that solar energy is actually being absorbed. Okay, so we notice that that water is a little bit darker. These mountains are white. Those clouds are white. So there's got to be some connection there. If our solar energy is being absorbed in darker areas and reflected in lighter areas. So here are these graphics. I don't expect you to show this graphic or this chart to your younger patrons, but it is helpful to know. This shows the amount of reflectivity in different surfaces. So we have all the way down here, water. It's going to be about 10%, 8%. It's going to absorb most of that solar energy. And we come up here and we see ice. Well, ice is going to absorb, 65%, so it's going to reflect 35%. And as we move up, we see these different types of clouds actually reflect and absorb different amounts of heat. And we see snow. Fresh, white snow is going to reflect upwards of 80 to 90% of the solar energy. So when you hear people talking about the ice caps and what kind of effect that would have if we didn't have ice caps, if we just had bare ground there, this is kind of what they're referring to. Those ice caps reflect back a lot of heat from our sun. And here's another little graphic. Again, just showing that an open ocean wouldn't reflect back very much, 0.06%. Bare ice, that would reflect back about 50%, and ice with snow about 90%. So you can see here, it's not just an anecdotal thing. It's not just, oh, I go outside and I'm hot. There is a lot of science behind it. So we're going to move the camera real quick. I'm going to pause it so you guys don't get motion sickness. So Jamie, if you would move the camera to focus over here. And we're going to try something kind of fun. I would normally do this activity outside, but it's going to be a little prohibitive during a webinar. So we've set up in here, and we have a parabolic electric heater. We have cleared it with our business office. Don't worry. We won't start any fires, hopefully. And so, Paul, I have two bottles here. Okay?
Yep.
Well, you notice they're different colors, right?
Yeah.
Okay. So I want you to just fill those balloons on the top. Do those balloons feel inflated?
Well, this one's slightly, but they're pretty deflated.
They're pretty deflated. Okay. Yeah. And what colors do we have here?
We have white and we have black.
We have white and black. And just so you guys know, I use some acrylic paint to paint these water bottles. And because as these balloons inflate, as it gets hot, they move around. So I've actually taped them to the top of this trash can. Okay. So if you're doing this outside, you might want to tape them down to the ground, just because they will move as they get larger and expand. So Paul, you said the balloons didn't feel that inflated. Maybe one is a little bit inflated.
Yeah.
So what do you think is going to happen if we put these in front of this heater?
Well, if I understand your albedo discussion, probably the black is going to be absorbing more of the solar energy.
Okay.
So it's going to, more so than this, which is going to reflect more.
Okay.
So there should be a difference in the air, I would think, inside of those.
Yeah. Okay. So you think maybe the effect of this black bottle absorbing more heat, it might actually heat up the air a little bit more?
Maybe.
Okay.
Yeah.
And so for all getting out of facilitator mode here, this is a two-part activity because we introduced the idea of albedo and that different color reflectivity. We also can kind of get into air pressure here because as this air heats up, it's going to start moving around a lot faster. And as it moves around faster in this closed container, these balloons are actually going to inflate a little bit. Now, for some kids, younger patrons, that might be a little bit complex of an idea to talk about air pressure and heat expansion or air expansion. So you can leave that off. You could just do this activity without without the balloons and just the bottles.
Nice.
And you could have the patrons.
The people are here.
Oh. Or you could do, and you could just have the patrons measure and feel how hot it is. So it depends on your age group.
You know, if you have sun outside, Brooks, you could imagine going outside, and sometimes we have, like in a parking lot, there's concrete or asphalt.
Right.
And sometimes, especially in libraries, they have these wonderful grounds. And so you can feel the same energy coming down. That it's way different if you feel that asphalt, how hot it can get.
Absolutely.
You know, and then if you feel the grass nearby, that feels kind of cool. And so that's a real That could be a nice little
Yeah,
way of that. The grass is absorbing the heat, and you're getting all that asphalt.
Absolutely. Yeah.
I mean, if there was, the other way around kind of a thing.
You can have your patrons go and do a little inventory around the library, like find all the dark spots, the lighter colored spots outside, and make that connection of, well, do you think if it was a hot day, would you rather be on this hot black asphalt, or would you rather be maybe in a green field or in a forest? So a lot of connections to make there. So I have set these on a trash can because which direction does hot air travel?
We think.
I think we think up. Yes. And I'm going to set these in front of this parabolic heater or parabolic electric heater.
At least hot air balloons function that way.
Yes. Yeah. Yes. And we're going to turn this on. Jamie is going to be our safety czar, make sure nothing catches on fire. Thank you, Jamie. And we're going to check back. Paul's going to talk a little bit more. We'll check back in maybe 10 minutes, 15 minutes. I have, talking about adding a tech time twist, I have this infrared thermometer. These are about, 15 to 20 bucks, somewhere around there. And for those of you that are worried about using these because of the laser pointer, you can turn the laser pointer off, or you can just cover the laser pointer with a piece of tape. These are a great investment. They can be used for so many different STEM activities, especially anything that's involving heat transfer. So
also making fudge. They're really good for making fudge.
Nice. I learned something. So we'll turn this on. We're going to check. After Paul gets done with the next part of this presentation, we'll come and check back and see what the results are. Or if the heater gets too hot and we're just like sweating over here, we'll interrupt and we'll come back and check. We were trying it out yesterday and we made it about 15 minutes and it was too much, so we'll see.
Brooks, is that a certain kind of heater that you have that's best?
Yeah, that's a great question. So there are different types of heat transfer, right? There's convective heat transfer, conductive heat transfer, evaporative, and so on and so forth. Jamie, could you mention a little bit of, this is your personal heater from
That's my personal heater, yeah.
From the early 80s, I think. And you said that this does mimic solar radiation.
Yeah, so this is actually a radiant heater, right? So rather than heating the air and letting that fill up the room and warm it up, this is actually generating infrared heat, which is why it's a parabolic dish. It actually focuses that heat. So it's like light, right? Except it's off in the infrared, and that's what we perceive as heat. So it's the same way the sun heats the Earth, right? Because the sun has to get the heat through space. So it's actually a pretty good analogy to what the sun's doing.
Yeah. All right. But ideally, you would do this outside. This is a good backup if you don't have a sunny day. But just keep in mind something like a heat pack, that might not work. Or, I don't know, some type of warmer. You need that specific type of heat. So, Paul, it occurred to me we didn't launch our first poll question, let's do this real quick.
Yeah.
And this is just basic Earth, Sun, scale, size, 101.
Yeah.
Go ahead and open this. How many Earths do you think could fit in the sun?
Interesting. I think I know the answer.
It's like you've studied this or something.
It's a good mathematics.
It is.
Fun mathematics kind of
And I feel like I usually give you guys
problem.
softball answers, but I actually made this one difficult. So instead of like 1, 10, 100, or 600,420, it's a specific, or it's a little bit more difficult. So I'm anxious to see what you guys choose.
Right.
I'll give you about 5 more seconds.
How many Earths could fit inside the sun? And of course, the Earth is pretty big. We think it's pretty big on our scale. But how many of our planet could fit inside our sun?
So it looks like most people, well, we're getting some good answers here all over the board. I'm going to go ahead and let's see, broadcast these results. The correct answer, Paul, would you like to give the correct answer?
Yeah, the correct answer, I say 1 million, but then I would go with the 1.3 million.
All right.
I just like to keep things kind of rounded off a little bit.
Yeah, right. 1 million might be a little bit.
It's easier to remember. And another way you can calculate it is that about 100 Earths side by side could be lined up, and that would go all the way across the diameter of the sun.
Okay.
So about 100 Earths there, slightly a little bit more, but about 100 Earths. So if it's 100 Earths in that dimension, and you do 100 times 100 times 100, that happens to be 1 million. So there's the math, if you want to do some math. And if you could tell that to some of the like middle school kids, if they'd be able to calculate, if they knew that 100 Earths lined up across the diameter, what does that mean? Okay, so I love that pole thing. I think the scale is so cool.
Oh gosh, I didn't have a chance to mention this. This is a kind of a text-heavy slide, so it might be best for you guys. I'll probably skip over this right now just for the sake of time. This is a sample program that one of our NASA at My Library participants did. And again, it's kind of text-heavy, so it might be good for you to read later. But this is Annalie Mills. She's in Henrico, Virginia. We went to the same college, Roll Tide, Annalie.
Wow.
And she did a program maybe a month or two ago, just kind of getting the interest built up. And so she just kind of listed out the flow of her program. I took a couple of things out, but I thought this seemed like a really, really great program. So she started with that video, and then she did something similar to our activity over here, but with construction papers. She talked about what a thermal shield was and that Parker Solar Probe thermal shield, and had her patrons kind of make their own thermal shields to see what stood up best to the heat. Nice. And then while they were waiting to kind of like let those thermal shields, yeah, Sandra, Amazon. Amy, do you have a good link for Sandra for an Amazon link for the infrared thermometer? While she was waiting for those results, she had her patrons use sinoculars, which we'll talk about in a little bit, to look at the sun, and she also used the Solar Vision app. So a lot of options here. I just wanted to show this to you. We'll make these slides available so you can go back and look at the sample kind of programming menu from Annalie.
And just a shout out to the blogs that we have up on the StarNet website, starnetlibraries.org website. There's a lot of library staff who are posting all sorts of amazing activities that they're doing and resources and links. So please either share a blog with us, or you can take a look at all these wonderful ideas that people are coming up with.
So Ann just linked to the eTech City
wow,
laser grip infrared thermometer.
That's a link.
Yeah,
that's the longest link I've ever seen.
Kate, I see your comment. I can't respond to that on the webinar. All right. So Paul, we're going to turn back over to you. You're going to talk about some of those connections between the Earth and the Sun.
Yeah, life on Earth, our existence and all of life on Earth would not be possible without the sun being what it is. I mean, its distance away from Earth is important. The amount of energy that it produces is really important. We could not survive without the heat and light. We're having a little bit of temperature problems on Earth right now, as Brooks mentioned, that as solar energy is reflected off of snow and ice very well, when that starts to decrease like it is in the polar regions, you're getting more absorption, and so things are starting to heat up, and we need to address that. But it's really an amazing equilibrium, almost a dynamic equilibrium that we have with our atmosphere. That blue thing that you see in this picture is the magnetosphere. It's this magnetic envelope that's protecting us, that surrounds Earth. So Earth is magnetic, and guess what? Our sun is magnetic. In fact, way more magnetic than Earth is. So let's go ahead, Brooks, and just look in more detail at the.
Paul, can I have a quick check-in?
A check-in.
Yeah, we're going to check in on our.
It's check-in time, everyone. Okay.
We won't get too motion sickness moving the camera. Bye.
So I just wanted to show them.
You can get a little bit closer to it. Yeah.
Wow, look at this.
I can't see that.
That's good right there.
Whoa.
Yeah.
This really is an amazing heat
source. Yeah, right?
Look at that. Look how.
So
whoa! Whoa!
Paul, which one? Do you feel any difference in temperature? The two of them? They both feel hot?
They both feel pretty warm, but I think this dark balloon here it's much tighter, if you will. Yeah, this is more squishy. That's not as squishy. I hope it doesn't pop.
So I wanted to do the check-in now.
Yeah. Oh, now.
So we got 103 on the. Let's see. 107 on the black balloon. And we got 94 on the white balloon.
Okay.
Makes sense.
Yeah.
So if you hear a loud pop, you'll just know that it's our balloons.
To our regular
back to the regular schedule.
Oh, that was cool. Thanks, Jamie. So let's go ahead and look. I think the next one is looking, inside the sun. Well, wow, you have all these different regions of the sun. Earth has, its own regions too. Like it has a core, but it's way different than the sun's core. That's way into the very center of the sun. The temperatures there are astronomically large, 27 million degrees Fahrenheit. Very hot temperatures. It's producing energy at an incredible rate through a process called fusion, which is fusing very light atoms like hydrogen and helium together, and they're producing these vastly powerful light rays called X-rays and basically gamma radiation in the core, and that slowly works out. It works its way out. The energy produced in the core of the sun. It's really cool, I think, to tell people that the energy produced in the sun, in its core, takes a lot of time to finally get out to the surface. So this is the cool fact. The light that you can see, if you go outside today, right now, and you feel that light bathing you, that light was produced in the core about 150,000 years ago, and saber-toothed tigers were roaming that early.
Wow.
There were early humans were around at that time, but 150,000 years.
So I know the 7 minutes from the sun's, from the sun to the Earth is how long it takes light to travel. So you're saying when I'm feeling this light right now, that originated 150,000 years ago in the core of the sun.
In the core of the sun. Now, it's going through all sorts of crazy interactions,
Certainly.
but then it goes into this region called radiative zone, and then it gets into a convective zone. And you've seen convection, obviously, in your stovetop. When you cook things like an egg, or when you do hard-boiled eggs and any soup and things like that, you see these currents that well up and then they go back down, and you get this big convective cycle of getting hot and then cooling down again. And that's called the convection zone, and that's kind of where the magnetic fields of the sun are really twisted up and formed, and you get all these huge structures that emerge from the surface formed somewhere in the convection zone. And then on the surface of the sun, many of you probably heard of sunspots. These are these regions that are larger than Earth. They're dark because they're slightly cooler than the surface temperature. If you remember the video, they said the surface temperature was about 10,000 degrees Fahrenheit. These are maybe like 7,000 degrees Fahrenheit. So I wouldn't want to touch one necessarily.
I don't think it matters what color shirt you're wearing.
I don't think it matters what color shirt. Exactly. And then you get this coronal region. That's the atmosphere, the outer atmosphere of the sun that extends all the way out past Earth and bathes all the planets. The solar probe is going to be looking at the inner boundary of the corona, which is really important because we don't know much about it. But we're in the atmosphere of the sun as we're orbiting this wonderful star of ours. And the photosphere is where the sunspots are. That's the nominal surface of the sun. But, it's a gaseous body, so it's hard to say what's a surface and what's not. It's certainly not a solid one. Okay, so let's go on to the next one. So here's a little animation. I don't think that's the right one.
Oh, yeah, you're right.
It's the sunspot one.
Bear with us.
That's okay.
And there's a link in the link bank again to not this exact video of sunspots, but a video of sunspots that you could show.
I love talking about sun-Earth connections. To me, it's just so cool. And this animation, we hope that it's going to work. Yep, way to go, Brooks. So look at the sunspots. One, that they're changing fairly rapidly. And the sunspots themselves aren't moving. They're moving with the surface of the sun, the photosphere. And so if you would calculate how long it takes the sun to do a complete orbit, which on Earth is how long, do you think? How long does for the Earth to spin once?
24 hours?
Hours, yes, absolutely. That's a day, day-night cycle on Earth. On the sun, the equivalent is about 28 days for the whole sun. But the sun, remember, is a little bit bigger than Earth, so that's still pretty impressive. Most of the planets are rotating, and the sun is also rotating. So that's really cool. So we're going to see, I think, some sunspots up close. There's one. Look at the comparison of Earth to this particular sunspot. You can see that the sunspot, and this is not a huge one either. Sometimes there's much larger ones, and you see the stuff outside the sunspot, all those little cellular features. Those are that's the convection that's happening. They're on these cellular structures that are cooling and getting hot, and you don't want to be on this. This is not a good place to vacation. I think it's even hotter than Georgia. I think.
How about Hawaii?
Oh, you mean with the volcano? Yeah, there's some convection going on there, isn't there, Jamie? Absolutely. So this is you can't really see it but these sunspots are very magnetic, and they go through this cycle of weak activity and very large activity. As I mentioned, in 2024, it's going to be a time of maximum solar activity magnetically, and right now we're at minimum or very close to minimum. Okay, let's go ahead and see some more features. Wait a minute. So who discovered and who found that that sun actually has sunspots? Well, it was Galileo when he used his telescope. And this is a great way to observe the sun indirectly. So you don't want to look at the sun through a telescope unless you have very special filters, like Ann Holland, I'm sure, would tell you, be careful, be careful, be careful. Check out everything very carefully if you're going to be peering through things that will amplify or enlarge images, because you don't want to hurt yourself or your patrons. But an indirect method like this is showing is really cool. This is a contemporary of Galileo around 1625. This picture was from. Okay, so I think magnetic loop. So we're going to be getting that. The sunspot is one form. We're going to show you now this pretty amazing video of the sun, I think taken from the Solar Dynamics Observatory, which is orbiting the sun much further away than the Parker probe is going to be orbiting. But look at that magnetic activity. I hope all of you can see it. It's pretty impressive. And there's all of these small scale features, all those bright spots, and the magnetic loops that are going from one to another. Underneath those are sunspots. Yeah. So this is a very active time on the sun when this was taken. And it just shows that the sun is really amazing. It has lots of magnetic activity going on. And we're going to show a few more. We're going to show some space weather from the sun. These are not solar flares so much, but we're going to show this hurricane of space weather called a prominence that erupts and forms these coronal mass ejections. So here's a much larger scale feature called a prominence, and you can see Earth to scale there. Not to distance, however, just size. Earth is not that close, remember. But you could see that many, many, many Earths could fit within and under that amazing arch. But it's kind of like the magnetic loop structures, and then it goes from one point to another. But it's just magnificent. Those are called solar prominences. And they can erupt, by the way. And they form sometimes these big, huge structures called the hurricanes of space weather are called coronal mass ejections. And millions, hundreds of millions of tons of particles and all that are launched from the sun, and they can impact Earth's environment and other planets as well. And that could disrupt electric power, could have problems for spacecraft orbiting close to Earth, that kind of thing.
Hey, can I interject?
Yeah.
So you notice the kind of funny, go back, Brooke.
Okay.
You notice the funny composition of that image with the sun inside that red ring. So that's because those coronal mass ejections are very faint. That corona is hard to see in the blinding light of the sun. That's exactly what you saw with the eclipse. If you were lucky enough to see totality, the moon blocked out the sun so that we could see the outer corona. But we have clever spacecraft that sit out in space, and they can make their own eclipse all the time that lets us see that corona.
Nice. They're called artificial eclipses, and it's very clever, just like Jamie says, and it's a wonderful way of looking out, not really close by. And again, that's why solar probe is so important, because you are eclipsing the inner part of the corona. Mm-hmm. You never see it because it's too bright. And so how can you do it? Well, we're going to send a spacecraft to look at that mysterious region that's eclipsed, if you will, in that image. And by the way, the coronal mass ejection is that huge bubble that you see extending out to the right of that picture and then down. So right and down to the right, down right. Okay, so let's go and look at, see one of these things, I believe, in motion. These are pretty cool events. Oh, you're using the April 1, okay, 2001. Mm-hmm. You can actually see this dynamically, and you'll see a bunch of particles all of a sudden, like salt or sand or something, hitting the spacecraft. Those are actual energetic particles that are hitting the instruments on board this spacecraft called SOHO. And it basically just lights up its noise in some sense to poor SOHO, but for us it's a manifestation of that this spacecraft was just hit by a storm of solar energetic particles.
It's kind of terrifying.
Yeah. And this is, by the way, super speeded up, so don't think that the sun does this in real time.
You can see the date and time.
Yeah. Exactly. Okay.
And I think in the link bank, I'll link you to a video of a coronal mass ejection from 2017 or 2016.
Nice.
So a more recent one.
Nice.
Yeah. Just hide it.
Yeah, the way that they do that, Jamie and Brooks, is just pretty neat. That these spacecraft can automatically do that. There's observatories on the ground here that do it, but being on ground is really tough because of the atmosphere and things. The spacecraft that are orbiting, say, a couple million miles away from Earth, still way closer to Earth than solar probe is going to go, are able to do these pretty clever observing methods that really has transformed our understanding of the sun, tremendously. And I like this little video here. This is an animation of kind of what is space weather and how does the sun impact Earth. And if it works well, it looks like it might. There we go. So this is going to be some event that happens, probably a coronal mass ejection that happens to occur from the sun. And it's going to go into interplanetary space from the sun to the Earth. And here it comes. And it's carried by the solar wind, which is going pretty fast. And then there's this interaction that takes place in Earth's magnetic envelope called the magnetosphere. Watch the pinching. Watch it. Here it goes. It's pinching. Whoa, boom. And now you get these accelerated particles guided along the field lines into the north and south polar regions. And we call those light displays, when they interact with the upper atmosphere, the aurora. And some of you might have seen the aurora on vacations or other places. This is kind of a cool picture looking down at the aurora from the International Space Station, Brooks. So that's kind of a neat way of looking at it. And all that light's produced in the atmosphere by these really high energy electrons that are streaming down because of this big interaction due to the sun. Isn't that kind of cool?
Really cool.
Yeah. All right, so there's another this is from the ground looking up. I don't know if anyone knows, maybe you can guess in the chat box, how far up do you think do auroras occur? Are they on the ground, just a little bit above you, or are they further up in the atmosphere? Why don't you tell us what you think in terms of miles away? So anyway, thanks Linda for saying that. Yeah, these are awesome pictures and videos. I just love them. In fact, we will be putting them on the StarNet YouTube channel. Some of them are already there, I think, but I will make sure that Greg get some of these animations like the sunspot ones and the other ones that you've seen. So that's called a corona, not to be confused with the sun's corona. People just like to be, I guess, confusing sometimes. But anyway, it's looking straight up at these particles streaming down at you. And if you're thinking about how far away they are pretty far away. These auroral lights occur about 70 miles above the Earth's surface. So they would be in space. You would be orbiting in that location, by the way. You wouldn't generally send up a rocket, though you could send up a sounding rocket that would study them. But they are pretty amazing, and all the colors are due to the different types of interactions, the different types of molecules in the atmosphere, and that sort of thing. I think those are the green is oxygen, for example, and I think the purple might be either some version of oxygen or it could be nitrogen. All right, so I think I am almost done.
Yeah,
I want to say thank you for giving me the opportunity to share with you some of the secrets and some of the magnificent behavior of our very own star, the sun.
Paul mentioned that solar wind earlier, so I just wanted to throw this poll question out there. What do you guys think the maximum speed of that solar wind is? Again, I give you very confusing answers to choose from.
Wow. I see. You have all sorts of, you have kilometers per second, Jamie, and then miles per hour. That's an interesting. And then kilometers per hour.
Miles
You
per
are
second.
terrible.
Tricky.
You are the
I just usually give them the softballs, 1, 5, or 3 million. So.
Oh my word! I think you should do, what is the old fortnights, or what's the, there's an English thing, Jamie, something about a furlong, in a fortnight.
These are nautical miles, by the way.
Oh lordy.
Oh yeah, Linda, we'll upload this on SlideShare, and then I can send it out to you guys as well. If for some reason you're not on the email list, please drop me a line, and I can get this to you as soon as possible. So yeah, you can have access to it. All right, we'll go ahead. You guys are all pretty close, pretty fast. The answer is 3 million miles per hour.
I wouldn't necessarily say it's maximum, because there have been cases where it's gone like 5 million miles an hour, which is very rare. Normally, I guess I would say 1 million miles an hour. I like millions. I like things that are, 1 million or 1 billion or something like that. So 1 million Earths could fit inside the sun is a pretty good guess, a reasonable number. 1 million miles per hour is kind of a reasonable number, I think, for the solar wind speed. And the solar wind bathes the whole solar system. It goes all the way out, way past Pluto and into the Kuiper Belt and beyond. And it finally ends its influence, I don't know how many AUs away. It's so far away. It's called the heliopause, this boundary where the sun's influence ends and interstellar space begins. Which is another thing that we'll have another webinar on interstellar space things, maybe at another time.
Random other factoid. So the Parker Solar Probe is named after Eugene Parker, right? Who put together the work of several people and made a model for predicting that there was such a thing as the solar wind. And according to the article I'm just reading, that paper, when he submitted it, was actually so controversial that 2 of the reviewers rejected it. And it was only saved for publication by the then editor, Chandrasekhar, who then later got his own Nobel Prize. So smart guys.
Smart guys, yeah. Eugene Parker, one of the fathers of modern day space physics, if you will.
All right, so Paul, I'm getting a little warm. I think we should check in over here so we can turn this dang thing off. Linda, yes, you do, of course, have permission to use this. I don't think there's anything in those PowerPoints that you couldn't use. So.
Oh, absolutely not. Yeah, absolutely not.
Absolutely not, as in, yes, you can use it, right?
Yes, you can use it.
Okay, great. So we're going to check in over on our balloons. We'll take a measurement reading. Oh, geez, it's hot.
It's hot.
All right.
Turn off those things.
So we can see, Paul, what do you notice about our balloons?
They're both of them, very. I think air in here has gone up into the balloon. Wow, that's pretty tight.
What about the other one?
What? you know, it's in there, but a lot less than. Boy, there's a big difference between the black one and the white one.
Okay, so do you think, to be consistent, we should measure maybe the temperature of the balloons?
Why not?
I think that would be the most consistent thing to do here. We got somewhere between 106 and 107 in this balloon. I think this is pointing directly at the, here.
Go from the side.
Yeah, go from the side. Here we go. Okay, what are we reading right here, Paul?
About 94, it looks like, and
Over here?
97.
Yeah, I think it's still picking up on some of this radiant heat.
They cool down pretty fast.
They do cool down pretty fast. So we'll come in from the top. We'll get 96 on the black one. And 95, so not that much of a difference. But if we measure the actual bottles, we're going to get, again, 95. Okay, so we're not getting a huge difference. We do have this, the heater right here, right next to us. So if we did this outside, we'd probably get a little bit of a difference. But I think we're getting a lot of this hot, radiant heat.
But Brooks, look at the difference in the bulbs.
Yeah.
I mean, in the balloons. That's the difference.
Yeah.
So that means that hot air is still in that black balloon, and the other one is now really deflated. I mean, it's now totally gone back.
You can
into
see
the
this one's
bottle.
starting to get that way.
Yeah. So
again, you know, this infrared thermometer makes it a lot more fun. It makes it a lot more techy. But just having students maybe feel the temperature and having that balloon there as the visualizer. So we are a little bit over. I do want to show you one more activity. This is called Nito Magneto. And I've showed this to you before. Jamie, why don't you just put the camera right here. Sorry, hopefully you guys aren't getting motion sickness. And then if you want to point it down, yeah, perfect. So this is a fun activity. I've highlighted this before, but I just thought it really kind of tied in well with what Paul was talking about in terms of those sun-earth connections. So here we have a standard, or it's like a styrofoam ball. So you could do either a styrofoam ball. We looked out and we found these that are actually, Earth globe styrofoam balls. So this works out really well. We also have this bag full of staples. So inside of this globe is a magnet. It's a pretty strong magnet with a north and a south pole to it. So when we put these staples, and this is not the whole Nito Magneto activity, this is just a portion of it. I think it's called magnetic globe. And so we're just going to kind of sprinkle these staples over it.
nice.
And as you do it, you have to work with it a little bit. But as we put these staples on it, and we kind of even them out, you'll notice that they travel in the Earth's natural magnetic field lines. So let me see if you can see that. So they all radiate out from the poles. And if you use a bigger one, it's a little bit more defined, but you can still see it traveling in those poles from north to south. Okay, so it's just an easy way to kind of model that Earth has this magnetic field. We use clamp staples for this. We looked at using iron fillings or BBs, and none of it really worked, and they all kind of presented some safety hazards. So this is actually the best way to do this activity.
I think so.
Where do you get the ball with the magnet inside? Linda, great question. You make it. You have to order the styrofoam balls, and then you order the magnets. It's not too hard. You just split it open maybe with like a little, you could even punch open a hole like with a pencil through it, or you could use a little, like some scissors to cut it open and retape it. So there's a few different ways to do it. The activity gives you instructions on how.
I bet kids might like to help do that.
Yeah, help if you made the holes for them and you had them stick the magnet in. Yeah, maybe some older.
Careful with the super strong magnets, though.
Yes.
Yeah.
Yes. And Jeanette, yes, you did probably get this activity in Kit B. So the last thing I want to talk about, and Jamie, if we could move it back out there, you've done a wonderful job. Thank you.
Well, thank you.
With all those advanced degrees, you're an excellent filmographer.
Way
Is you guys probably did a lot for the eclipse, and you probably still have a lot of eclipse stuff hanging around. So these wonderful solar glasses are not just for the eclipse. These are for all the time. You can go out, as long as you have taken good care of them, you can go out and you can still observe the sun with these. Now, of course, you're not going to see the actual eclipse happen, right? There's not going to be any eclipse, but you can see the sunspots, and it's pretty cool just to put them on and go out and look at the sun. So I would say maybe try to find when the next big sunspot cycle is. I gotta take these off. And go out, if you have solar eclipse glasses that you know have not been scratched and have been protected, have your kiddos or whoever, even your adults, go out and observe the sun. Also along those lines, we have these sinoculars. Same thing, these are like solar eclipse glasses, but a little bit more advanced. And Annie Holland can tell you a little bit more about these. I forget exactly what these are. Lunt sinoculars, so you can just get a better view of the sun. Thanks, Jeanette. With these. Let's see, the Solar Vision app. I don't have a visual for that or anything, but that is an app that we have developed here at SSI. Is it just called Solar Vision, Jamie? Yeah, and you can model your own eclipse, and then you can apply different filters on the sun to get a real-time view of the sun. So you could use Solar Vision, pull up that image and say, oh my gosh, there's a big sunspot right now. Let me use my sinoculars or my solar eclipse glasses and go and look and see that actual sunspot. So that is called Solar Vision. And another fun activity, scale model of sun and earth. We've done this a lot, and it does apply to the eclipse, but it also is just a good idea to get, or a good activity to get an idea of scale for your patrons. You have a big printout like this with the sun on it. And you can't see it, but the earth is very tiny right here. So you have your patrons cut out these things, or you can cut them out ahead of time, and they try to guess how far away should you be to be an actual scale model of the sun and earth. We have a YouTube video. You can click on that how-to video of this activity. Yes, Jennifer was wonderful to core those and put the magnets inside. If all of you libraries could have a Jennifer to do that with the Nito Magneto, you'd be in luck. Anyway, check out the YouTube video. This is a fun, easy, really cheap activity. All you have to do is print out things, and it kind of blows people's mind when they realize how far away the sun and earth are. And then indirect solar viewing, I've linked to an activity there. That would just be like a pinhole projector or a shoebox projector. Again, can get you a really good view of the sun, even though it's not, time for the solar eclipse. All right. Well, Paul, we did it. We were only a little over. And
sorry about that.
Oh, that's fine. It's the best way to spend your time learning about science. So we'll move over to our Q&A pod. I know some of you guys might have to go get back to your circulation desk. I know we've lost some folks already. But if you guys have any specific questions for me or Paul, I think we have our whole staff online right now too, so we can answer any type of questions that you might have. Oh, good, Kate. I'm glad to hear that. I hope I didn't make your blood boil when I told you I went to Alabama. And this, like I said, we'll get this up maybe in about 2 days. So feel free to share it with any colleagues, any library colleagues that might benefit from this or are planning on doing STEM programming.
One thing too, I know that Greg has a wonderful website on starnetlibraries.org, and it's all about the Solar Probe mission. I believe it has hopefully a link to that video, yes, and maybe some other cool resources. There's probably things for libraries to download and to print. There's all sorts of, obviously there's great connections to the STEM activity clearinghouse for activities. So, and I don't know what to do about that launch window issue for libraries. That is somewhat of a troublesome thing. But, make it, maybe instead of having it lemon, make it into lemonade, where you're doing an activity for the upcoming launch, and even though you're not necessarily seeing the actual launch of the spacecraft, you can be prepared for it and get all of your patrons excited so that maybe they can stream it.
Here's an idea. You could do something like if you do an activity that day and it doesn't actually launch, you could do stomp rockets, but then you could throw in some variables in there. So maybe spray a hose on the stomp rockets, and you say, can you launch off when it's raining or something? I don't know, it's a terrible idea. You guys are clever. But yeah, you could...
disappoint everybody.
You could kind of...
Sandra, yeah, let me just respond to that. They will be, all of there's a mission website that I believe Greg has up on the Solar Probe page on our StarNet site. And you can go directly to the mission page, and they will be posting all sorts of things on that. In terms of, are there going to be delays? I think when they say a launch window starts July 31st, that's what they truly mean, that could actually launch on that date. I think that's generally when they want to launch. But, again, there's lots of variables.
I would say NASA social media feed's great too. They provide a lot of updates on Twitter and things like that. So definitely worth a follow.
Yeah.
Launch first. That's true. It can be a minute-to-minute decision. So it is.
I think that the recent test launch to Mars actually was delayed a couple days, was it not, because of weather?
Oh, the InSight launch.
The InSight launch. Yeah.
Yeah, and it doesn't take much. I mean, I was at the Ares launch, and it was just high clouds. That was all
High
it
clouds.
took for them
Yeah.
to cancel. So.
Right.
And if that clears off, and within, because there's, besides that big window, there's probably a daily window.
Yep.
So, they'll wait over that hour or whatever on a given day,
Right.
and then they have to slip to the next day.
Exactly.
Greg, if you're online, if you could send Lisa a link to sign up for the newsletter, that would be wonderful. And we'll give it a few more seconds. If anybody else has any more questions, feel free to put them in there. Otherwise, as I mentioned, next week we'll be doing a webinar on community dialogues. So how you can bring important members of the community to your library and have an awesome discussion about what your community needs are, specifically how that relates to STEM.
It's a wonderful partnership building opportunity. It's a framework. Ann Holland is taking the lead on that, and I'm helping her. Greg is too. So we should have a website ready to go, we hope. It's very close to have all these great resources for these partnership building kinds of opportunities.
Mm-hmm. And the week after that, it's the Girls Steam Ahead with NASA resources. The week after that, the Universe of NASA resources. So we have a lot of resource dissemination webinars coming up for you. And then, like I said, we'll probably take a lot of June and July off just for you guys in summer reading, and we'll be at ALA and other conferences. And then kick back off in August with a whole new, whole bunch of webinars for the fall. All right, well, I think it's time to wrap things up, Paul. I appreciate you being here. Jamie, I appreciate you running quality control over there. And until next time, we will see you later. And you'll be sent to a survey. When I close out the room, it'll send you to our Survey Monkey. If you could fill that out, we would really appreciate it. We'd love your feedback.
Thanks, everyone.
Thanks, everybody.